Hello everyone, welcome to video lecture series of design of steel structures. We are dealing with unit number 5, design of welded plate girder. In the previous two videos we have seen introduction to welded plate girder, what are the different conditions of D by TW ratio for design of welded plate girder depending upon the requirements of stiffeners, and we have also seen first condition, numerical condition 1, when D by TW ratio was equal to 67 or less than 67 epsilon. So these particular cross sections are designed as a regular flexural members when your D by TW ratio is equal to or less than 67 epsilon. So in this particular video we are going to see condition number 2, when D by TW ratio is going to be in between 100 to 200 and your section may be subjected or it may be failed in shear buckling, and there may be requirement of your end bearing stiffeners at the supports. So just we'll start with the video. The numerical statement for the video is given as: design a welded plate girder of span 24 meter laterally supported throughout. The beam is 24 meter span and it is laterally supported. It has to support uniform load of 100 kN per meter. UDL is given 100 kN per meter on entire span exclusive of self weight. Design the girder without intermediate stiffeners. So as it is written, it is without intermediate stiffeners. There is a requirement of end bearing stiffeners. The steel grade for flanges and web is Fe410. Design the cross section and end bearing sections, stiffeners and connections. So in the numerical itself, the given data is already highlighted. Span is given, uniformly distributed load UDL is given, it is excluding the self weight. Intermediate stiffness requirement is not there. Again, steel grade is given as Fe410, and you have to design the cross section, end bearing stiffeners and the connection. So in the given data, span we have already discussed, and loading is to be multiplied with 1.5 partial safety factor. So the total loading will be now 150 kN per meter. So initially we need to calculate the self weight as it is excluding. So total load into span divided by 200 is the value. So 150 into 24 by 200, we are getting 18. So therefore the total load will now be 168 kN per meter acting on the span. So here is the correction. This is as per last numerical only, therefore it should be near about 168 kN per meter. Just make this correction. So now total uniformly distributed load on the span is 168 kN per meter, and again it is uniformly distributed load, therefore maximum shear force will be Wu into L by 2, while your maximum bending moment will be WL square by 8 value. So calculating the values, we are getting shear force as 2016 and bending moment as 12,096 kN meter. Now you can observe the values of shear force and bending moment acting on the section. Tremendous amount of movement is coming on the cross section as the span is greater and loading is also greater. So almost you should design a cross section in order to sustain shear force of 2016 kN and bending moment of 12,096 kN meter. So after calculating bending moment and your maximum shear force, plastic section modulus is to be calculated in regular flexural member sections. Here you directly calculate the economical depth for the given cross section or for the given bending moment. So as we are knowing that economical depth depends upon your D by TW ratio, and that is nothing but K factor, and K factor we are selecting depending upon the requirement of stiffener. If the stiffeners are not required, you go with K value as less than 67 or up to 67. When stiffeners are required only at the ends or above the supports, you provide a value between 100 to 200, and when stiffeners are to be provided at intermediate span also, you provide your D by TW value in the range of 200 to 270. So according to the statement in the numerical, stiffeners are required only at the ends or end bearing stiffeners are required. Therefore select D by TW or K value in the range of 100 to 200. So suppose for this numerical we'll assume value as 180, D by W will assume as 180. So economical depth required, so cube root of value movement into K factor divided by Fy. So we are getting almost value 2057.42, and I am round figuring that value to 2060 mm. Now as again we have assumed D by TW as 180, you can calculate the thickness, and the thickness is equal to 12 mm. So 11.44, that is round figure to 12 mm. Therefore you need to provide a web plate of size 2060 by 12 mm. So this is the size of web plate decided. Similarly, now calculate the area of flanges required according to the same formula. Already in condition 1 also we have seen this. So area of flanges required is equal to area of flanges into Fy into depth divided by gamma m0 equals to your moment, equating with maximum moment. We are getting near about 25836.11 mm square. So 25,836 mm square. Now again, the flanges to be in plastic, we are generally approximate value of 0.3 to 0.4 times of your depth value. So we'll add up near about value 618 round figure to 620, and again equating it with area required, you are getting flange size as 620 by 42 mm. So likewise, by equating with maximum factored bending moment, we have finalized the cross section. The cross section will be two flange plates of 2060 by 12 and web plate of 2060 by 12 and flange plates of 620 by 42. So this will be the cross section. Now initially classification of cross section, classification is plastic, and your web will not be in plastic or semi compact as we are adapting slender section. This is not going to satisfy the conditions, but as it is a plate girder for economy, intentionally we are doing this so that economy will be achieved and there will be provision of stiffeners. So only classify your cross section depending upon your flanges. So that is plastic. So calculating moment of inertia. So moment of inertia, again Ig plus AH square, applying your parallel axis theorem and finding out horizontal perpendicular distance between two parallel axes. So initially BD cube by 12 into area into h square. So h in case of this will be 2060 divided by 2 plus 42 by 2, and that is almost equal to 1051 square. And second, BD cube by 12 for 12 web thickness multiplied by 2060 cube divided by 12. So this is going to be your moment of inertia about z side. Similarly, you calculate moment of inertia about y side also, dB cube by 12, and for dB cube by 12 h parallel axis is not there, therefore your value of h is going to be 0, only moment of inertia is to be considered. Now similarly calculate extreme fiber distance, y bottom y top, total depth divided by 2 value. Calculate elastic section modulus and calculate plastic section modulus with the help of shape factor. Now shape factor value is directly 1.14 for rectangular sections. So now calculated plastic section modulus we are getting as 70.39 into 10 raised to 6 mm cube. Now as again the classification is plastic 1, plastic section modulus is also known. You can calculate the design bending moment for laterally supported type of girder. So that is beta b into plastic section modulus into Fy divided by gamma m0, and I am getting near about 16,000 kilonewton meter. 16,000 kilonewton meter, that is 515,997. So almost equal to 16,000 kilonewton meter, and it is greater than your required value 12,096 kilonewton meter. Therefore the selected girder is safe to carry the factored bending moment. Now next step, as we have applied or we are using end bearing stiffeners, your shear buckling capacity of web is to be calculated. Now this is the difference in the condition. According to clause 8422 page number 59, shear buckling check is to be given only if the stiffeners are provided. If stiffeners are not provided, in that cases your shear capacity of web is to be calculated with regular calculation, that is design shear capacity of your web by using VD formula, and for VD you need to calculate it with the help of shear area into Fy divided by root of 3 into gamma m0. So this was the formula up till now we were adapting, as stiffeners were not adapted. For the numericals, when stiffeners are to be adapted, in that cases the shear capacity of web is to be calculated using clause number 8422, and either it can be calculated using simple post critical method or it may be calculated using tension field method. So using one of the method only you can calculate these values. So initially suppose we'll adopt simple post critical method. Now again, if you observe simple post critical method from page number 59, initially your elastic critical stress is to be calculated. So elastic critical stress depends upon the KV factor, and KV factor depends upon the types of stiffeners adapted. whether the stiffeners are provided only at ends or the stiffeners are provided at intermediate span also. Now, as in the given data for this numerical, we are adapting stiffeners at end supports only, or we are using end bearing stiffeners. According to page number 59, kV value is going to be 5.35 compulsorily, as only EBS are used. If we are using IS, that is intermediate stiffeners, in that cases your kV value is going to be vary, and that depends upon your C by D ratio or spacing of stiffeners and depth of stiffeners. So that particular part we are going to cover in next video. So here, as end bearing stiffeners are used, your kV value is going to be 5.35. so putting the value for critical stress calculation, critical shear stress calculation, kV is 5.35 into pi square, E is modulus of elasticity 2 into 10 raised to 5 divided by 12 into bracket 1 minus mu square, mu is 0.3 divided by D by TW ratio. So D we are knowing, and thickness of web that already we have decided in first steps. So direct 2060 by 12 square, almost we are getting 32 MPa, 32.81 MPa. Now this calculated value of elastic critical shear stress is to be put in for next formula to calculate your lambda value, that is slenderness ratio for your web. So that is under root of Fyw divided by under root of 3 into tau c TC area value. So that is already calculated in the first step, and now we are getting that slenderness ratio up to 2.097. So according to this calculated value of lambda del W, whether it is greater than 1.2 or less than 1.2, we are getting greater than 1.2 value, and based on that you are calculating the tau b, that is shear stress value. So tau b will be given as Fyw divided by root of 3 into gamma w square. So above calculated gamma w value, root of 3 and Fyw is 250. Now I am getting your tau b shear stress value as 32.82 MPa. Now calculate your shear buckling capacity. Vn is equal to Vcr, that is Av into tau b value. So Av is total depth 2060 into 12 value multiplied by 32.8233. So this is the value, and we are getting capacity, shear capacity as 811.39 kilonewton. Now here you can observe that this calculated value is less than your maximum capacity. This value is less than maximum capacity 2016, therefore it is failing in shear capacity of web, or shear buckling capacity of web is lesser one. Therefore the capacity of web is to be increased, and either you revise the web thickness, and here you can add up the thickness as next value, either you go with 16 mm, or for reducing your calculation you directly add up 18 mm. So in next you adapt thickness of web as 18 value, and again adapt these particular formulas of simple post critical method and calculate your value. Now only there will be change in this particular D by TW ratio, rest values are going to remain same. Instead of here TW was 12 value, we have revised it to 18. Rest calculation will be same, and now you can check that our value of Vn is equal to Vcr, which was previously 811, is now 2737.61 kilonewton. Now as this value is greater than 2016, our shear buckling capacity is satisfied, and you can go for the further calculations. Now this is compulsorily understood. If it was condition number 3 and our value was lesser, that is shear capacity of web was failing, in that cases this shows us the requirement of intermediate stiffeners. But as in the statement it is mentioned not to adapt intermediate stiffeners, we have revised the thickness of web. So if you are not going to improve or increase the thickness of web, simply you can provide intermediate stiffeners also. Now check for web buckling FWB, already same formula we have seen. FWB is given as area effective into FCD. Area effective is plate bearing width into thickness into FCD. So we'll assume, suppose plate bearing width of 150 mm, and for single dispersion D by TW value is there. So overall depth divided by 2 plus 150, we are getting 1222, and thickness is 18. And now lambda depends upon, so lambda depends upon I by under root of I by A value, and lambda is KL by R minimum. So for R minimum you are requiring under root of I by A value. So moment of inertia for that 150 plate bearing width, so it will be equal to BD cube by 12, 150 into 18 cube by 12 divided by 150 into 18. Now I am getting, so here is again one correction, instead of I it should be R. So R I am getting 5.19 mm, and KL value is nothing but 0.7 times of depth. So 0.7 into depth I am getting 1442. Take the ratio KL by R, that is 277.84. Now if you observe buckling class C and table number 9C, the values are limited up to 250 only. Maximum slenderness ratio according to table is given 250 value. So here, as we are getting value greater than 277.84, you can calculate it with regular calculation which are mentioned in section 8 of IS 800. So initially calculate FCC value. So FCC is given as pi square E divided by lambda square. So that value pi square E divided by lambda square value is there, and for that lambda value we have already calculated. E is 2 into 10 raised to 5. I am getting lambda value, sorry, I am getting value as 25.57. Now based on this you calculate lambda as under root of Fy by Fcc. So that is 3.12, and alpha is always 0.49 for rolled section. Phi calculations, so phi requires 0.5 into 1 plus alpha into lambda minus 0.2 plus lambda square. So putting the values and performing the calculations, I am getting FCD value as 20.11 MPa. So almost very less value is there, 20.11 MPa. So FW will be now calculated area 1,222 into 18 multiplied by FCD 20.11. Now that force value is only 442.33 kilonewton, and almost this value is also less than 2016, which is the maximum shear force acting. Therefore this fails, and this shows that there is requirement of end bearing stiffeners. As the buckling strength of wave is not satisfying the requirement of maximum factored load, there is requirement of end bearing stiffeners. So the required or remaining value will be capacity minus factored shear force. So capacity is 442, and your maximum value is 2016. Therefore difference of 1574 is there, and for this you need to design your end bearing stiffeners. So from width of flange you can define what is the maximum outstand possible. So it will be 620 minus 18 divided by 2, 301 mm. So maximum outstand can be provided is of 301 mm. So suppose we'll assume that we will use stiffeners of size 300 by 18. So this outstand will be 300, and again from this side also outstand will be of 300, and this particular core section is always 20 times of TQ value. So outstand should not be greater than 20 times TQ, and outstand should not be less than 40 times TQ. According to it, you should select the value between 252 and 360. You have to adapt value intermediate of this 252 and 360. Suppose we will adapt value as 300 mm. So I am using end bearing stiffeners on both the sides of your web of size 300 by 18, 300 by 18. So now area effective can be calculated 2 times 300 into 18 as on either sides plus your core area. So core area is 2 times 20 TQ. So 2 into 20 into 18, and into thickness of web is 18. So this area is 23,760 mm square. So this orange color area is a core area, and that area is value is 23,760 mm square. Similarly calculate moment of inertia about Z side. So again BD cube by 12, and H value is will be distance between perpendicular distance between two parallel axes. So that will be equal to 300 by 2 plus thickness of web by 2. So it will be equal to 159 square. So total value of moment of inertia I am getting as 81.41 into 10 raised to 6 mm raised to 4 moment of inertia. So initially calculate under root of I by A for radius of gyration. So that is 58.53. Calculate KL by R, 0.7 into depth divided by R value 24.63. So round figuring it to 25. Now you referring buckling class C, table number 9C, FCD is 217.5. So for this calculated FCD and area effective, you can calculate the force. Now this force after providing your end bearing stiffeners is almost 5167 kilonewton, and that is greater than your difference value 1574. So if you are going to provide stiffeners on either sides, your cross section is capable of taking force 5000 kilonewton, and almost this is subjected to only value 2060. Therefore the selected end bearing stiffeners are safe to carry or transfer your required shear force. So likewise the design of end bearing stiffeners will be completed. Now this will be the cross section. Web portion 2060 by 18, and your flange cross section will be 620 by 42. Now this will be the elevation, side elevation. This will be your plan. And intermittent welding, so design of connection is not shown here. This is similar with last numerical only. You can just copy down that particular steps. Only remember, in case of your girders, your welding is to be provided as intermittent welding, because throughout welding is not possible for given span of 24,000 or 24 meters. So likewise the numerical will be completed. In the next video we will be starting with condition number 3 numerical. Thank you.